Hi everyone. We are gonna dive into this paper from iClear 2019 called the lottery ticket hypothesis. It's been a while since it was introduced, but I think it's still highly relevant because it forms the basis for a lot of research today. So this is going to be a discussion into the general idea behind the paper, the motivation, and some takeaways some ideas that you could potentially use are just good to know. So here we go. If you've heard anything about neural networks, you know they can be incredibly massive with millions, even billions of parameters. And here's the thing. We have these amazing techniques called pruning that can take fully trained networks and chop away over 90% of its connections without losing accuracy. That's fantastic for making models smaller and faster for deployment. But here's the paradox. If we can make a network so small after training, why don't we just train that smaller network from the beginning? Why not save all that computational effort? The problem, as observed in contemporary experience, is that the sparse architectures provided by pruning are difficult to train from the start. Training a pruned model from scratch typically performs worse, suggesting difficulty in training networks with small capacity. It seems like training a dense, over-parameterized network is somehow easier. So this brings us to the lottery ticket hypothesis. Here we go. They made a truly surprising finding in this paper that dense, randomly initialized feed-forward networks containing subnetworks, which are considered winning tickets in this context. So these subnetworks, when trained in isolation, reach test accuracies comparable to the original network in a similar number of iterations. Think of it like this. Your randomly initialized network is a big pile of lottery tickets, and only a tiny fraction are winning tickets, because their connections have initial weights that make the training particularly effective. These are the lucky ones who won the initialization lottery. Let's formalize this a bit. Imagine you have a big dense network. Here, F is denoting that, and it's initialized with random parameters, theta naught. When you train it, it reaches some minimum validation loss, L, at iteration j, with test accuracy A. Now, the hypothesis states that there exists a small subnetwork defined by this mask on your original parameters, which you can represent as this product between the mask and theta naught, such that this subnetwork, when you train it, then it reaches a accuracy that exceeds the initial accuracy A and uses around the same number of iterations and needs significantly fewer parameters. So how do you find these winning tickets? The algorithm is quite elegant. You randomly initialize your full dense network F, then you train this network for a given number of iterations to get the parameters theta j. Then you prune a certain percentage of the parameters, typically the smallest magnitude weights. This gives you the mask M that defines the structure of your winning ticket. And then this is the crucial unique step. You reset the remaining parameters to their original values in theta naught. This new sparse network, which they represent as this term over here, this is your candidate winning ticket. The paper also focuses on iterative pruning, where you repeatedly train, prune, and reset over multiple epochs, which helps find even smaller winning tickets. The key insight here is that structure alone isn't enough. Let's look into where they discuss this. Right. So when they took a winning ticket structure, but randomly reinitialized its weights, it no longer matched the performance of the original network. This offers strong evidence that these smaller networks do not train effectively unless they are properly initialized. They go through a significant amount of discussion regarding specific networks that I will skip over. Beyond speed and accuracy, winning tickets also showed improved generalization. They often exceed the original network's test accuracy while maintaining its training accuracy, meaning the gap between training and test performance is smaller. This suggests what they call the Occam's Hill phenomenon, which is cited from another paper from 2001, where the original overparameterized model might be too complex and extremely pruned models too simple, with winning tickets striking that optimal balance that you need. One fascinating insight comes from observing how the weights of winning tickets change during training. You might think they stay close to their initial values if they're so well initialized, right? But the opposite is true. The winning tickets weights move further than the other weights from their initial values during training. This suggests that the benefit of the initialization isn't that they're pre-trained, but rather that they're well placed in the loss landscape for effective optimization by the chosen algorithm and dataset. This all leads us back to this lottery ticket conjecture that SGD seeks out and trains a subset of well-initialized weights. And here's the kicker. Dense randomly initialized networks are easier to train because there are more possible subnetworks from which training might recover a winning ticket. It's not that dense networks are inherently better at training, it's that they provide a richer search space for the optimizer to find that well-initialized subnetwork. So what are the implications of this? We can hope to design better training schemes that find and prune winning tickets earlier. We can also design better networks and initialization schemes, taking inspiration from these winning tickets, and fundamentally, it offers a new perspective to improve our theoretical understanding of neural network optimization and generalization. In conclusion, the lottery ticket hypothesis reveals a fascinating hidden structure within our deep neural networks. It tells us that success isn't just about throwing more parameters at a problem, but about finding those specific well-initialized connections that are destined for efficient learning. It's a powerful idea that reshapes our understanding of how deep learning works and opens exciting new avenues for making AI more efficient and effective. Thank you for tuning in.